All right, welcome to the testing portion of the 2022 Delaware Bridge Design Competition. We are going to be testing the Conrad School of Sciences bridges. We're going to go ahead and get started with the little bridge that couldn't. Paul's going to go ahead and give us a weight in grams. 46 grams. So this bridge weighs 46 grams. One thing to note with this bridge is, for obvious reasons, we're going to have to disqualify it because we're not allowed to have a bridge deck, and we're definitely not allowed to have cardboard. But for posterity's sake, we're going to go ahead and load this bridge just out of curiosity to see what it could possibly hold. So I'm going to drop our testing rod down in there, and we will go ahead and get started with the loading. Just want to gently tighten this so that it's not picking up any load just yet. And make sure that it's barely tight. I don't want to waste any load. All right, so zero the machine out, and then we go ahead and begin testing the little bridge that couldn't. So we are at 2.72 kilograms. As I continue to turn, we've bumped all the way up to 4. One thing to note, that the two modes of failure for a bridge would be whether the bridge breaks or whether it meets its deflection limit. The machine is kind of governed by a certain amount of rotations. And this is something that we see in real life too. We would limit the deflection of our actual bridges. So it's not something that's out of the ordinary. As I turn, we're all the way up to 7.71. You can see that the bridge is actually starting to slide a little bit off of the pedestals. You can hear some light cracking. From where I'm sitting, I can see the bridge is actually kind of racking, but it is still picking up load. It's at 9.07. I don't know if you guys could hear that big crack. That was that main arch right there that just snapped. We're going to try to keep picking it up. As the bridge begins to break, it's important to note that the current force will drop, and you have the potential to pick up additional force, but it's not guaranteed. So right now, as I'm turning, the peak load is still holding at 9.07. As I continue to turn, we're still at 9.07. You can hear the bridge cracking. It's really breaking right now, and we have reached the deflection limit. So 9.07 would be the peak load. Paul's going to type this in and give us a ratio.
We have 197.17.
197.17 for the strength to weight ratio. All right, we are back with Conrad testing the second of, I believe, 18 bridges. We have insert team name here. Unfortunately, we also had to disqualify this bridge because it doesn't quite act like an arch. There was some back and forth, some discussion about whether the members, really were an arch. And unfortunately, this turned out to be acting more like a truss, like a regular truss system. Unlike the other bridge that had the cardboard bridge deck, this one isn't fully disqualified. It will be penalized, and the highest score it could receive is 50% for the bridge testing portion. So with that, Paul's going to go ahead and give us a structure weight.
We have 30 grams.
So the insert team name here bridge is 30 grams. Now we're going to prepare it to be loaded. Again, I'm going to try to get the testing rod, the load rod, centered on the bridge. I want to make sure that all of the bridges are loaded the same way. Make sure that we're not creating any eccentricity on our bridges. So barely tighten that down, and now we are ready to test. Zero the machine out, And away we go. So again, two main forms of failure. The bridge is either going to break or it will reach its deflection limit. We are at 3.18. Seems to be holding pretty well. 4.08. That last spin bumped it all the way up to 6.35. Can hear some light cracking in the structure, but nothing too major at the moment. We are now at 8.16, 9.07 for peak load. That spin, we're at 10.43. You can hear the whole structure is really starting to crack now. Still holding at 10.43. All right, it's picked up some additional load and is at 11.34. The bottom cord has snapped clean in half. And this is kind of what we were talking about. This bridge is not acting like an arch, because if that were to happen, the bridge would have automatically failed. We are still at 11.34. Still holding there. Bridge has continued to deflect and has now reached the deflection limit of the machine. So we have maxed out at 11.34 kilograms. And Paul's going to type that into the score sheet, and he's going to give us a ratio for the strength to weight.
We have 378.
All right, so strength to weight ratio for insert team name here of, say that again, Paul?
378.
378. All right, continuing on with Conrad's bridges, we are here with MKH. So Paul's going to go ahead and give us the structure weight.
We have 24 grams.
24 grams. With that, we're going to go ahead and get this thing loaded. So again, we're going to make sure we're centered, get everything positioned as clean as possible. Machine 0. Okay, so we're going to zero everything out, make sure we're in the right units. We are ready to start loading. All right, peak load of 3.18 right now. Oh, we've already heard a crack. It's holding at 3.18 at the moment. It's picking up a little bit of load. You can see some of the deflection. All right, now it's starting to pick up some load. We're at 3.63. Can really hear some cracking. This bridge has deflected and it's lost its tightness. Let's see if we can thread that down a little bit. All right. We are not carrying any load, and that is because we have lost this center cord right here. This portion of the arch has broken, so the bridge is not able to pick up any more load. So unfortunately, this bridge has a peak load of 3.63 kilograms. The important thing is that it did act as a deck arch truss. All right, so Paul's typing that in. He's going to go ahead and give us our ratio.
We have a ratio of 151.25.
All right, a strength to weight ratio of 151.25. All right, continuing on with bridge testing, we've moved on to Team Harvey from Conrad. Paul, go ahead and give us the structure weight.
We have 27 grams.
27 grams. Okay, so now what we're going to do is get the bridge set up again, get it situated. There we go. Just pick up a load. Okay. Make sure that this is zeroed out, and we'll start the testing. All right, Team Harvey, let's see what you got. 1.81 right now. Still loading. We're starting to pick up load. We're at 3.63. 4.08. Continuing to go, we're at 5.44. Just heard the first crack. I don't know if you could hear that on the camera. 5.9. The center cord that the block is resting on has snapped in half. So we're gonna try to see if we can pick up any more load. Looks like we may be at about the limit. So one of the things that we have to consider when we're designing our bridges is making sure that, you know, all of our members are sound. You can see that this bridge didn't actually fail. It was just the block that the tester was sitting on, the cords that the block was sitting on. So yeah, we have reached a peak load of 5.9 kilograms. Paul's gonna type that in and give us our ratio.
We have 218.52.
All right, Harvey is in with a strength to weight ratio of 218.52. All right, moving on to Team Chester from Conrad. Paul, what do we have for a structure weight?
We have 21 grams.
21 grams, so a little lighter, that's good. All right, let's get it into the tester. Get it situated, centered. Okay, zero it out, make sure we're in the right unit. Let's go ahead and start loading Team Chester. All right, 1.81. Holding at 1.81. See some light deflection on the cord that the block is sitting on. 2.72 is where we're sitting right now. Got up to 3.18. Haven't heard any pops yet. 3.63 is the max load so far. It's holding at 3.63. It just jumped to 4.08. It is worth noting again that as the bridge takes on load, it'll shift and deflect some, and it'll cause the current load to drop some. So the peak load, it has to pick back up. So we're sitting at 4.08, 4.54. We're still just deflecting. The bridge seems to be holding strong. It hasn't broken. 4.54 seems to be the number to beat. Oh, we heard our first crack. And it just reached the deflection limit for the bridge. And it has a peak load of 4.99 kilograms. You can see how much the bridge is actually deflected, but it didn't actually break. So Paul, what do we got for strength to weight ratio?
We have a ratio of 237.62.
All right, Team Chester with a strength to weight ratio of 237.62. Team Bad Piggies is up now. Paul, why don't you go ahead and read off the structure weight?
We got 30 grams.
30 grams. All right, let's get it in the testing apparatus. Make sure we are set. Ooh, just touched those cords. So one thing to consider is how you're going to load the block in the future. This one is barely touching from end to end, so it's just worth noting. Fortunately, this was spaced in a way that is not letting us load it directly in the center, so it's only hitting one support. So this is probably gonna take on a little bit too much load for one member, but we'll see what happens. All right, so we've zeroed it out. We're in the right units. We're gonna go ahead and start loading the Bad Piggies bridge. You can see the block is already sitting askew because it's only resting on one cord. But we're up to 1.36, still loading, 1.81, and unfortunately that one has just broken. So the bridge itself never actually got to fail. That top cord failed, And because it was only resting on that one piece, it didn't actually work. So unfortunately, the peak load for this is 1.81 kilograms. Paul, what is the strength to weight ratio for this?
It is 60.33.
All right, Bad Piggies with a strength to weight ratio of 60.33. We decided to reload the Bad Piggies with a different block, just for posterity's sake. We wanted to see what happened when you actually break the bridge. So we used a larger block, and we're going to retest it. This won't count towards the official score, because obviously the 2-inch block was a guideline and requirement for the bridge testing. But just for the sake of failing the bridge, let's see what it can do. All right, so I'm going to go ahead and load it. We're already at 2.87. We have moved up to 4.99. So it's far exceeding. The bridge is much stronger than its initial load. We're at 7.26. We've heard our first crack. Can't tell what member. Oh, one of the end members popped off. And now the bridge can no longer hold its weight because it's got nothing to rest on. So unfortunately, it's just going to keep sliding down. So we peaked out at 7.71 kilograms. And if Paul, if you type that in, what would that have been, just in case?
That would have been a ratio of 257.
257, and that would have put you into the lead for the time being, but unfortunately, part of the requirement is the 2-inch testing block. Team ROYGBIV is up next. I enjoy that team name. Paul, what do we have for the structure weight?
We have a lightweight, 19 grams.
19 grams. That could play an important role in the strength to weight ratio. All right. So we actually had to offset this because, fortunately, the bridge, try to flip it, the bridge has a center cord right where the testing block should go, the testing rod. So we're going to offset it just a little bit. Shouldn't make a big deal. Make sure that's backed off. Zero out the force. We are ready to test ROYGBIV. Let's go ahead and start turning. 2.27, 2.72. Holding at 2.72. We made it to 3.18. Hearing some light cracking. We're at 4.54. 5.44. Oh, we've started to break. Okay, so 5.44 seems to be what we're holding at. We'll see if we can pick up some additional weight, but guess is the peak load is going to be somewhere around there. Holding strong. Yep, the structure just fully broke. So the peak load is 5.44 kilograms. And Paul, that equates to a strength to weight ratio of
286.32.
286.32 for ROYGBIV. Up next, we have Team Atlas from Conrad. Paul, what's the structure weight?
We got 26 grams.
26 grams. Not the lightest, not the heaviest. We'll see how it does. Drop this testing rod in here. Go, zero that. Make sure we're in the right units. We are ready to test Team Atlas's bridge. We are already up to 1.81, 3.18, 4.9, 5.9, 6.33. 7.26 seems like it's doing all right. 8.62. Oh, we heard something pop. Looks like the center cord has broken. So see if we can pick up some more load as we go. Right now we're at a peak load of 8.62. That may be the peak load that we end up with. feel the machine tightening a little bit. Let's see if we can get back to exceeding that peak load. I can hear the bridge cracking. Doesn't look like we're going to get there, but all right. So we have a peak load of 8.62, which should be one of the higher loads we've seen for Conrad. Paul, what does that put us at strength to weight ratio?
331.54.
Okay, Team Atlas with a strength to weight ratio of 331.54. Next up, we have Balsa Boys Reborn. There's a nice looking structure here. What do we have for structure weight?
We also have 26 grams.
26 grams for structure weight. So let's see how it does in the testing machine. Let's go. We've said this once or twice before, but the two ways that the bridge can actually fail will be if it breaks or if it reaches its deflection limit. All right, so Balsa Boys Reborn, we're going to start the loading. Peak load right now, 4.54. Seems to be picking up strength pretty quickly. We can feel it. The machine's getting a little tighter. 8.62. 9.98. We're in the double digits, 10.89. Oh, and a catastrophic failure. But we reached a peak load of 10.89. The bridge failed. And it's interesting, the bridge itself, again, didn't fail. It's that top cord where the loading block sits. So what was our strength to weight ratio, Paul? The 10.89 peak load.
We got 419.
419 strength to weight ratio for Balsa Boys Reborn. Coming back at you again with Balsa Boys Reborn, just like with one of the other structures, we were curious what it could actually hold if the top cord didn't break on the loading blocks. So this won't count for the official score, but we were curious to see what this thing was capable of. So we're going to start loading it. Just going to ramp it up. Obviously, we're using a longer block, so it's loading much more of the top cords. And we're already at 13.6. We've made it all the way. I can hear a lot of cracking. Seems like we're going to max out at 15.88. Yeah, you can see it's failed all the top cords now. Yep. All right, 15.88, which would be a strength to weight ratio of
610.
610. That would have been great. So one of the things that's worth noting is these top cords between your main structure seem to be what's failing. So possibly if we had narrowed the bridge so that the loading block sat right on these long cords, maybe you'd start to see some higher numbers. All right, just like with the Balsa Boys Reborn, we brought back Team Atlas. We wanted to see what they were capable of because they did a pretty solid job. Again, it doesn't count, but we're curious. This is the bridge nerd and Paul and I coming out. So we're up to 8.62 already, 11.79, 13.61. It's doing a nice job here. 14.97. We are at 17.69. And that seems to be where it's failed. All the top cords have now failed. So 17.69 would have put them at a strength to weight ratio of
680.
680. What could have been?
Could have been.
But room for improvement, and that's how we learn. So overall, nice job. Next up, we have 3 of a kind. Paul, what's the structure weight?
We have 21 grams.
21 grams. We've trimmed some of the fat here. All right, let's get it situated. They need the testing block, that's for sure. Okay, looks like they've time beefing up the center, this area where the loading block is going to sit. Check our units. Zero it out. All right, we are ready to test 3 of a kind. All right, we're already at 6.8. Light cracking, 9.5. Okay. Oh, we have deflected the bridge. Some of these cords you can see have disconnected. So we're holding at 9.8. We'll pick up some more load. 9.98. You can hear the structure starting to really crack. Yeah, it's pretty wild. All right, it has lost a lot of its load. It's nowhere close to the peak load, but it really did a nice job there. And we are at holding at 9.98. And that's where it's going to stop. Yep. All right, so 9.98, it was pretty light. So Paul, what is the strength to weight ratio?
That is 475.
475 for 3 of a kind. All right, we're about to test big Thrax. Paul, what's our structure weight?
We got 25 grams.
25 grams, so kind of middle of the road for what we're seeing from Conrad weight-wise. Let's see how it does load-wise. Zero this out, make sure we're in the right units. We are ready to load. Here we go. 2.27, 3.18. Can see a little bit of deflection in the center. 4.99, 5.9. Holding at 5.9. Seems like the center cords are starting to break a little bit. 6.35. 6.8, and that was a big snap there. Not sure what snapped. Any idea?
Looks like maybe this just came unglued.
Oh, okay, it looks like the truss portion came unglued from the top cord. So we're starting to break. We've lost a lot of force here. We're not getting back to that peak load yet. Maybe we'll be able to load it and pick that back up. Does it look like it? Nope, we have reached the max, 6.8 kilograms. We're just continuing to crack.
That is strength to weight ratio of 272.
272 for big Thrax for strength to weight ratio. All right, we are going to be testing the 3 Musketeers and Seth. Seth, again, I'm sorry that seems like you were an afterthought in the team name here. So what weight did we have for the structure?
We got another lightweight at 19 grams.
19 grams. We've seen the lighter structures, even if they don't hold a lot, it does help a lot with the strength to weight ratio. So that we kind of equate that in the real world of bridge design to an efficient structure. You know, we can design a bridge to hold as much weight as we possibly want, but is it necessary? Is that something we really need out of our structure if it's never going to see those kind of loads? So kind of think of it from an efficiency standpoint. All right, let's get it tested. Zero everything out. We're in the right units. 3 Musketeers and Seth. Here we go. 2.72, 3.63. Start to hear some cracking. 4.08. Okay. 4.54 seems to be the number we're at right now. Nope, we're hearing some popping. Seems like this is, you can see the bridge is starting to warp a little bit. It's still holding that peak load. Get it. Now it seems like it's broken. The cord that the block is sitting on. All right, we are at 4.54. Okay, 4.54 seems to be the final load. Paul, what is that?
That is 239.
Strength to weight ratio of 239 for the three Musketeers and Seth. Now testing the Felders from Conrad. What do we have for a structure weight?
We got our lightest one yet, 15 grams.
15 grams. All right. Went for a sleek aerodynamic look here. Let's see if it pays off. The one thing that I think will work to the benefit of this bridge is that the block, instead of resting on these cords that are running sideways, is really going to be loaded directly on these outside pieces. So it may actually let the bridge pick up a decent amount of weight. And you won't have to worry about these top cords being, the weakest link. But we'll see. That's my speculation. Okay. Zero it out. We are loading the Felders. 3.63. 6.35. 7.71. We heard a pop. I'm not sure where it broke, but we are at 8.16. Here's some big pops here. You can see it breaking. Oh, it looks like it broke right where it's connecting here. See if we can get it to pick up a load. Looks like 8.16 is going to be the number for them. But with that light structure, you may see a pretty high strength weight ratio. You can see the bridge is really starting to crack here. All right, go ahead, Paul. Why don't you fire off that number for us?
We got 544.
544. So it didn't hold the highest load, but it was very light. So that really did help it in the strength to weight ratio department. All right, we are testing Beaver Boys from Conrad. Okay, what do we have for a weight for the structure?
Yeah, 18 grams.
18 grams, another light one. That's good. Let's see how it holds. The wide structure here. Sure, we're centered here. Hopefully, we're all set. Okay, zero it out. Make sure we're in the right units. Start to see a pattern with that. Okay, loading 1.81 is where we're sitting right now. 2.27 hasn't picked up a ton of load yet. Seems to be deflecting pretty easily, and that's the issue. 2.72, 3.18. Here we go. Starting to pick up some load. 3.63. I haven't heard any cracking. We're holding, oh, there it goes, it's jumped. 4.08, 4.54. And unfortunately, we have reached the end of the deflection here. So the bridge has deflected past where we would say is an allowable deflection. So we have a peak load of 4.54 kilograms. You can see how much it's bowed. What does that equate to from a strength to weight ratio, Paul?
That is 252.
252. All right, so we're back again with Beaver Boys. We decided to go with a longer block. Obviously, this won't count for official scoring, but we wanted to see if we could break the structure instead of just bending it. So let's see what we can do. Sitting at 2.27. It's picking up load a little faster than it was with the 2-inch block. We're at 4.08. holding at that. Oh, it is racked the bridge. You can probably not see it, but from where Paul and I are sitting, the bridge is actually kind of twisted and it's no longer picking up any load. So it actually did better with the 2-inch block. Maybe some cross supports across the bottom here would have helped it stay a little bit more stable. All right, next bridge structure. This is the second to last bridge. This is the bridge trolls. What do we have for weight here?
We've got 26 grams.
26 grams. So we're back up to a little bit heavier of a structure. Also went tall for this one. Okay. One thing we have seen some of the teams do from Conrad to pretty good effect is use this little step here to kind of press against the pedestals, and that kind of it almost wedges itself in there and is able to pick up load. And that is really how an actual arch works. So that's one thing to be mindful of. Make sure we're centered here. We're good. Zero out. We're in the right units. Here we go with the bridge trolls. 4.08. It's picking up load quickly. 7.71. All right. We're already at 10.89. Oh, 14.06. 16.78. This is exciting. 18.61. Still picking up load. Can we get into the 20s? We're at 19.05. All right, still at 19. Here it's really started to bow out towards the camera. So maybe some of this height is working against it a little bit, starting to buckle. The load is backed off. We're down in the 10s now. Seems like we've lost the load. We're down to 7. The peak load here is still very high. Picking some load back up, but I think we're going to run out of deflection limit. Yep. So peak load of 19.05 kilograms, and that's going to equate to what?
733.
733 strength to weight ratio for the bridge trolls. Very nicely done. Final Conrad team to be loaded is the failing torpedo boats. During their presentation, they explained that this was just a random bunch of letters that they typed into a program and it spit out a team name. So pretty interesting, but I digress. What do we have for structure weight, Paul?
We're at 25 grams.
25 grams. So we're back to being a little heavier, but we'll see. Much more narrow from a height standpoint. The one thing that is very interesting to see is, again, this is the exact width of the bridge. So in theory, all of the load should be transferred straight down these side members, these side trusses. Good. Cool. All right, there we go. This is the failing torpedo boats, and they are already at 4.54, 6.35. So again, it's picking up load fairly quick. 7.26, 8.16, 8.62. Seems like the center of the bridge is deflecting. So that arch, because it's not using these pedestals to push off of, is kind of kicking out. And you're seeing that arch buckle. Whereas if they had possibly put that ledge in there, you would see it really resisting and pressing back against this. So we're at 9.07, 9.53, still picking up load. 9.98, and we have reached the max deflection here. So we peaked out at 9.98 for the failing torpedo boats, and that equates to a strength to weight ratio of
399.
399, a very respectable score.